All right, now we're ready to talk about inverse functions. So inverse functions can be generated from functions that are one-to-one. That means not only does every x correspond to exactly one y, but also every y belongs to only one x. This function is not one-to-one because we see two different points where we have the same y value but two different x's. So that leads us to the horizontal line test. Remember, a vertical line test told us if we were dealing with a function. The horizontal line test tells us if the function is one-to-one. If I pass a horizontal line across the graph of the function and it intersects in no more than one place, then the graph is a one-to-one function. All right, so we want to determine is x cubed one-to-one. What we would do algebraically is substitute in two different x values, x1 and x2, and look to see if they are the same. Notice that I cannot have both of them be the same value when I cube them unless I started with the same value. Therefore, it's one-to-one. Graphically, we would pass horizontal lines over the graph, and we intersect in no more than one place. The graph is one-to-one. We're interested in one-to-one functions because those are the functions that have inverses that are also functions. We define the inverse. We read this as f inverse. Remember in the previous section we said like x to the negative 1 is 1 over x. But when we apply that negative 1 exponent to a function, we don't mean a reciprocal like this. We mean an inverse. Okay, so we're double using notation here. The inverse is defined like so. F inverse of y being equal to x is equivalent to saying f of x is equal to y. In other words, the inverse function goes backwards from what the function does, okay? So if my function maps x to y, then the inverse maps me back to x. So in other words, the inverse undoes whatever it is that the function does. The domain of f inverse is the range of f. We act on the y here, right? So it's the range. And the range of f inverse is the domain of f, right? This is what goes into the x. It's the output of the inverse, though, okay? So the domain and the range, this is an important property here. The domain and the range flip places between a function and its inverse. Okay, so if I have the function f of x equals x cubed, its inverse is x to the 1/3 power, because when I run f through f inverse, it gives me back just an x, okay? So I said this already, and then we got that, okay. So, for example, if f of 1 is equal to 5, and f of 3 is equal to 7, and f of 8 is equal to negative 10, f inverse of 7, we're going backwards. So f inverse of 7 is going to give me a 3. F inverse of 5, we're going backwards. It's going to give me a 1. F inverse of negative 10 is going to give me an 8. We're going backwards, okay? All right, so this is a diagram that shows the relationship between a function and its inverse. Remember that the domain and range change places between a function and its inverse. Here is our definition again. This is showing a way to check if two functions are inverses of one another. We just discussed this a second ago. If I run one function through the other and I get back just plain x, those two functions are inverses. All right, so we see that with x cubed and x to the 1/3. We compose this way, we get just x. We compose this way, we get just x. That means those two functions are inverses. So how do we find an inverse from a function? Here are our steps. We're going to go through this with an example. Okay, so the first thing that we do is write y equals square root of x minus 3. Then flip our x's and y's. X equals square root of y minus 3. Add 3, because we're trying to solve for y. So we get x plus 3 is equal to square root of y. To undo the square root, I have to square both sides. And what I get is y equals x plus 3 squared. We know that x plus 3 squared is a parabola that's been shifted left 3. So that's at negative 3. That's symmetric, okay? All right, is that one-to-one? Well, if I pass a horizontal line, nope, I have two different x's that generate the same y. So we have to put a restriction on this. We have to say x has to be greater than or equal to -3, so that I'm only taking half the curve. What that essentially does is that erases this half, so that I'm only looking at this. Now, if I look at square root of x minus 3, right here, sorry, that's a square root function that's been shifted down 3 units, right? So it would look like this. So now notice that there's a symmetry between the two functions. If I dot in the line y equals x, those two functions are symmetric, okay? This is true of all of our inverses. That's this property right here. They're always symmetric about the line y equals x. So I can obtain the graph of f inverse by flipping the graph of f across the line y equals x. All right, this brings us to our logarithmic functions. So the logarithmic functions are the inverses of exponential functions as defined by this relationship. You need to memorize this. You need to be able to go back and forth between a logarithmic statement and the exponential equivalent. Okay, so for example, if I'm looking to solve log base 10 of 0.001, then I would say, what power of 10 do I have to raise what power do I have to raise 10 to generate 0.001? And the answer is a -3. So that's the way that I go about evaluating a logarithmic statement. Now, because they're inverses, the composition both directions cancels and gives me just x. So that's these two properties right here. Log base b of b to the x simplifies to just x. They undo each other. And b to the power log base b of x. Again, they undo each other and you get back just x. A logarithmic function has this shape to the graph because we're reflecting the exponential over the line y equals x. So for my logarithm function, the domain is 0 to infinity and the range is all real numbers. That matches what I'm expecting between the relationship of a function and its inverse. The domain and range flip places. If we remember for the exponential b to the x, the domain was all real numbers and the range was 0 to infinity, and we can see that here, okay? So those flip places between a function and its inverse. Now, also on the graph of the exponential, we had a horizontal asymptote at y equals 0 right in here, right? Because this is getting closer over here. So that makes a vertical asymptote over here. So on the graph of this guy, we have a vertical asymptote at the y-axis, the line x equals 0. Some of our laws of logarithms that you learned in college algebra, again, you should have these memorized. Remember that your logarithm is an exponent. It's the exponent to which the base must be raised to generate what's inside the log. So these follow the rules of exponents. If we are multiplying two items with the same base, we add their exponents. Dividing, we subtract the exponents. A power to a power, we multiply the exponent. So you can remember the logarithm rules that way. We can use those laws of logarithms to evaluate this expression, log base 2 of 80 minus log base 2 of 5. I can first put those together as a division, log base 2 of 80 divided by 5, which is log base 2 of 16 if I work out that division. So now I'm asking the question, what power do I have to raise 2 to make it a 16? In other words, 2 to the something equals 16. And the answer there is 4. Okay, natural logarithm. We talked about the natural exponential function. That was base e. So the natural logarithm is a logarithm base e. Instead of writing log base e of x, we write it as ln of x. This is the equivalent back and forth between the two. So again, our composition properties, ln of e to the x simplifies to x, and e to the ln of x simplifies to x. Ln of e is just a 1. All right, we can use these properties to solve for x. So now notice that if I rewrite this as an exponential statement, I'd rewrite it as 5 minus 2x equals e to the -3. So I would subtract 5 and get e to the -3 minus 5, divide by -2 to get x by itself, and we get x is equal to 5 halves minus e to the -3 over 2 if I just flip the order of the numerator with the negative sign. We'll start with the next example on the next video.